children, hearty welcome to today's class. Last class, we stopped there in the cleansing action of detergents. Today, in this session, we are dealing with the consequences of surface tension. We have 3 points as a consequence of surface tension. The first one is the droplets can have the shape of the spherical shape. The second one is capillarity and meniscus formation. Third one is water spreads on glass but mercury remains as a drop. Now, let us see each consequences one by one. First, we will discuss about spherical shapes of liquid droplets. This is the first consequence, that is spherical shapes of liquid droplets. We know that because of the surface tension, the liquid at the surface will try to reduce the surface area. Since the liquid at the surface molecules try to reduce the surface area, the molecule will attain a spherical shape because the spherical shape is having the minimum surface area. Then the second point is that when two liquid drops come together, it will join together and form a larger drop because the larger drop has minimum surface area than the two liquid drops. If we consider two liquid drops, one liquid drop has one surface area, another liquid drop has another surface area. So, it will, when these two come together, the surface area will be larger than the larger drop. Therefore, the liquid will acquire the larger drop when two liquid drops come together. So, here we have the points why the first consequence, that is the spherical shapes of liquid droplets. The surface tension tends to reduce the surface area to a minimum. For a given volume of liquid, a sphere has the minimum surface area. That is the one point. A sphere has the minimum surface area. Hence, a liquid drop tends to assume a spherical shape. If two drops encounter each other, they tend to join together and form a larger drop because one larger drop has a small surface area than two small drops. That is, if we have one drop here and another drop here, when these two drops come together, we will get a larger drop because this larger drop is having the minimum surface area compared to the two small drops. This has minimum surface area. Okay, I hope you understood the first consequence, that is spherical shapes of liquid droplets. Now, let us see the second consequence, that is capillarity and meniscus formation. This also depends on the surface tension of a liquid. Capillary tube is a glass tube which is small diameter. That means the capillary tube is very thin tube. When this capillary tube is dipped in a liquid, according to the nature of the liquid, the capillary rise or fall will happen. That is the capillary action. That is, if we explain this little more, here we have water. Suppose this water is in a beaker and here we have a beaker. In the beaker we have water and we are dipping one small capillary tube here inside the water. This is water. When we dip this small capillary tube in a water, after some time we can see the capillary rise. That means the water in the capillary is increasing. Initially it was here only, but after some time we can see the capillary rise. This is because of the adhesive forces between the glass and the water molecules are stronger than the cohesive forces of the water molecules. I will explain little more this one. That is, the glass is made up of silicon dioxide. Here silicon dioxide having the structure, tetrahedral structure. This the glass is made up of silicon dioxide and we have water here. So, we know that water like this. Here so many water molecules are there and the glass also made up of so many silicon dioxide. And this, when this silicon dioxide, that means when this glass and water will come together, there will be a strong adhesive forces between the oxygen of the silicon dioxide and the hydrogen of the water molecule. Therefore, this is adhesive force. That means the force between two different molecules, that is between the silicon dioxide and water molecules. We know that the water molecules are having strong hydrogen bonding. Here we have hydrogen, then here we have another water molecule. This oxygen of this water molecule and hydrogen of this water molecule is having an interaction, and this force is called cohesive force, that is the force between the same molecules. Okay. So, here the capillary rise is due to the higher adhesive force of silicon dioxide and the water molecules than the cohesive force of water molecules. Because of that, the capillary rise is happening in the when the glass tube is in contact with water. Okay, I hope you understood this one. I will explain once again. When the liquid, when water is in contact with the glass tube, what will happen? The adhesive force between the glass and the water is higher than that of the cohesive force of water molecules. Because of that, the capillary rise is happening. Capillary rise means because of these strong adhesive forces, the water from the beaker will adhere into the capillary tube and the water in the capillary tube will increase. The water in the capillary tube will increase. Initially it was here, then because of this adhesive forces, the water in the capillary is increasing. Okay. Then the next thing is that the meniscus formation. Meniscus is nothing but the curved surface at the liquid and solid surface. Here in capillary rise, the concave meniscus is forming. This is the concave meniscus. The concave meniscus is forming. Because of the capillary action, concave meniscus is forming. Then the concave meniscus means here the edges will be upward and at the center it will be downwards. That is concave meniscus. Okay. Then we have a contact angle here at the concave meniscus. This angle is called contact angle. This angle is theta. This is less than 90 degree. This is about the capillary action when water is in contact with the glass. The second case is that When mercury is in contact with the glass, capillary fall will happen. We will see what is the reason of that. When mercury is in contact with the glass, the bond between the adhesive forces between the mercury and the silicon dioxide is smaller than that of the metallic bond existing between the mercury molecules. Because of that, the capillary fall is happening. I hope you understood. I will repeat once again. That is, when mercury is in contact with the glass, the cohesive forces between the mercury and water molecule is less than that of the, this is adhesive force. The adhesive force between the mercury and water molecule is less than that of the cohesive force between mercury molecules. That means the cohesive force of mercury molecules are stronger. Because of that, the capillary fall is happening when mercury is in contact with glass. Here we are getting a convex meniscus. That means the center will be upward and the edges will be downward. Because of this strong metallic bonding, the mercury in the beaker also will get some concave meniscus here. Okay, this is about capillary rise and capillary fall. And this is the angle which formed here in the convex meniscus, that is greater than that of 90 degree. This angle is greater than that of 90 degree and this angle is less than that of 90 degree. Then we can conclude that for capillary rise shown by wetting liquids. Wetting liquids means when water is in contact with the glass, the angle will be, theta will be less than 90 degree. That is concave meniscus. For capillary fall shown by liquids that do not wet glass, then theta will be greater than 90 degree. That is when glass will be in contact with the mercury. Okay. This is about capillary action and meniscus formation. I'll repeat once again. When water is in contact with the glass, the bond between the adhesive forces between the water molecules and the glass, that is silicon dioxide, will be stronger than the cohesive forces of the water molecules. Therefore, the capillary rise will happen. That means the water in the beaker will adhere through the capillary tube and the water in the capillary tube will rise. That is capillary rise. Then the angle, the meniscus will be concave meniscus and the angle will be less than that of 90 degree. When mercury is in contact with the glass, the metallic bond between the mercury molecules will be higher than that of the adhesive forces between the mercury and water molecules. Therefore, the capillary fall will happen. Because of this capillary fall, there will be convex meniscus occurring and the angle will be greater than 90 degree. This is about the second consequence, that is capillary action and meniscus formation. Now, let us see the third consequence, that is water spreads on glass while mercury remains as a drop. Water spreads on glass while mercury remains as a drop. This is the third consequence. This difference is because of the surface energy. We'll explain this in terms of surface energy. Here, this is the solid surface, and the liquid is resting on the solid surface. When the liquid is resting on the solid surface, this theta is the contact angle. Then this is the interface. Here we have air, that is gas, and here we have liquid, and here we have solid surface. And this is the gas solid interface, because here gas is there, here solid is there. So this is gas solid interface. We have here liquid and here solid, therefore this is liquid solid interface. Here we have gas, here we have liquid, therefore here we have gas liquid interface. Okay, and this gamma is the surface tension. This gamma is the surface tension. At equilibrium, all the forces acting at the interfaces must balance. That means the gas solid interface, the force at the gas solid interface and liquid solid interface and gas liquid interface must balance. The surface energy, gamma Gs, that is the surface energy at the gas solid interface, gamma Ls, that is the surface energy at the liquid solid interface, and gamma Gl, that is the surface energy at the gas liquid interface. At equilibrium, the surface energy at the gas solid interface is equal to the surface energy of the liquid solid interface plus surface energy at the gas liquid interface into cos theta. This is the Young-Drupe relation. That is, the Young-Drupe relation is gamma Gs is equal to gamma Ls plus gamma Gl into cos theta. Young-Drupe relation is gamma Gs is equal to gamma Ls is plus gamma Gl cos theta. This is Young-Drupe relation, that is at equilibrium the surface energy at the gas solid surface is equal to the surface energy of the liquid solid interface plus the surface energy of gas liquid interface into cos theta. This theta value, that is the contact angle, theta is the contact angle, and this theta depends on the values of surface energy of the gas solid interface and surface energy of the liquid solid interface. The contact angle theta depends on both values, two values, that is the surface energy of the gas solid interface and surface energy of the liquid solid interface. Okay, that means if the surface energy of the gas solid interface is greater than the surface energy of the liquid solid interface, then the cos theta value will be positive. That means theta is less than 90 degree. The cos theta is positive. That means the theta is less than 90 degree means the cos 90 less than cos 90, all that will be the positive values. That means the cos 30, cos 0, all that values will be positive. So when theta is less than 90 degree, cos theta is positive. When this surface energy of gas solid interface is less than the surface energy of the liquid solid interface, that time the theta value will be greater than 90 degree, that time cos theta will be negative. Okay, I repeat once again. When surface energy of gas solid interface is greater than the surface energy of liquid solid interface, that time the theta will be less than 90 degree. Then the cos theta is positive. When surface energy of gas-solid interface is less than surface energy of liquid-solid interface, that time theta is greater than 90. Therefore, the cos theta value will be negative. When glass on water, the surface energy at the glass-water interface is less than that at the glass-air interface. That is the first case when this is the case when glass on water. This is the case when glass on water. That is, the surface energy at the glass-water interface is less than that at the glass-air interface. That we can say that gamma, the surface energy of GS, is greater than that of surface energy of liquid-solid interface, and theta will be less than 90 degree. This is when glass on water. When glass on water, the theta will be less than 90 degree, then the liquid will be the water will spread. Here water will spread because the theta will be less than 90 degree. That means the surface energy of gas-solid interface is greater than the surface energy of liquid-solid interface. When glass on mercury, what will happen, or in the case of mercury, what will happen, that is the second case, that is the surface energy of gas-solid interface is less than the surface energy of liquid-solid interface. In other words, we can say that the surface energy at the glass-mercury interface is greater than that at the glass-air interface. That is, theta is greater than 90 degree. Here, this theta is greater than 90 degree. This is the case when mercury is on glass. When mercury is on glass, it will be as a drop. But when glass on water, it spreads because there theta is less than 90 degree. Here theta is greater than 90 degree. When theta is greater than 90 degree, what will happen? The surface energy of gas-solid surface is less than the surface energy of liquid-solid interface. That is the case when mercury is on glass. When glass on water, then the theta will be less than 90 degree. That is, the surface energy of gas-solid surface is greater than the surface energy of liquid-solid interface. This is about consequence, that is, the water spreads on glass while mercury remains as a drop. This is also the consequence of surface tension, that is based on the surface energy, or explanation is based on the surface energy. Now, till now we were discussing about the consequences of surface tension. We had 3 points. The first one is the spherical shapes of liquid droplets. Second one is capillary action and meniscus formation. And third one is water spreads on glass while mercury as a drop. Now, let us see factors affecting surface tension. We have 3 factors which affect the surface tension. The first one is temperature, second one is impurities, and third one is nature of the liquid. First one is temperature, second one is impurities, and third one is nature of the liquid. Let us see these factors one by one. First, we will discuss about temperature. When we rise the temperature, the surface tension decreases. That means we know that the molecules are arranged like this in the case of liquid, and the surface molecules are having some inward pull, that is nothing but the surface tension, and because of this inward pull there is tension here at the surface. Then if we increase the temperature, what will happen? The kinetic energy of the molecules will increase. The kinetic energy of the molecules will increase. If the kinetic energy of the molecules increases, means the intermolecular attraction decreases. Because of the speed, the intermolecular attraction decreases. If the intermolecular attraction decreases, there won't be that much inward pull towards the interior. Therefore, the surface tension will be decreasing. Okay, I repeat once again. When the temperature increases, what will happen? The kinetic energy of the molecules increases inside the liquid. When the kinetic energy of the molecules increases, what will happen? The intermolecular attraction of the molecules decreases. If the intermolecular attraction of molecules decreases, automatically the inward pull that will be decreases. That means the surface tension will be decreasing. Okay, I hope you understood this factor, temperature. Okay, this we can explain one by the equation, Ramsay-Shield equation. This is the equation which relates the surface tension and temperature. Surface tension and temperature. This is surface tension, that is gamma, the surface tension and temperature. The equation is, Ramsay-Shield equation is gamma m by rho power 2 by 3 is equal to k into Tc minus T minus 6. Gamma into m by rho power 2 by 3 equal to k into Tc minus T minus 6, where gamma is the surface tension at Kelvin temperature T and rho is the density of the liquid and m is the molecular mass, k is a constant, Tc is the critical temperature and T is the temperature at Kelvin. Here, when T is equal to Tc minus 6, here if you look, when T is equal to Tc minus 6, what will happen? This term will become 0. That means the surface tension will become 0. When T is equal to Tc minus 6, what will happen? The surface tension will become 0. Therefore, in order to avoid this, Katayama modified this equation, and this equation is gamma m by rho minus rho slash is equal to k slash into Tc minus T. This is the Katayama modified equation, that is gamma into m by rho minus rho slash is equal to k slash into Tc minus T, where rho dash is the density of the vapor at temperature Kelvin. Here we have one table which shows that the decrease of surface tension as the temperature increases. At 0 degrees Celsius, the surface tension of water is 7.57 into 10 power minus 2 Newton per meter. At 15 degrees Celsius, it is decreasing, that is 7.35 into 10 power minus 2. At 20 degrees Celsius, it is again decreasing, that is 7.275 into 10 power minus 2. This is about temperature. The second factor is impurity. That means if some impurities are there on liquid, what happens to the surface tension? The presence of other substances increases the surface tension. That is based on the, if we have pure substances, the surface tension will increase. If we have amphiphilic substances like oil or other surfactances, then the surface tension will decrease. Okay. Impurities means If we have pure substances, the surface tension will increase. If we have amphiphilic substances like oil or surfactants, then the surface tension will decrease. Pure substances means if we have some sodium chloride, sugar, glycerol, all that things in water, then the surface tension of water will increase because the intermolecular forces will increase, because here we have sodium chloride, sugar, all that things are there. So, the intermolecular attraction, electrostatic interaction also is there. So, the intermolecular attraction increases. If the intermolecular attraction increases, automatically the surface tension will increase. If we have amphiphilic substances, then the surface tension will decrease, because the surface, we have already seen this in the cleansing action of surfactants. That is, if we have the surfactants are having the hydrophilic part, and hydrophilic part is attached to water, and it is having a, the surfactants is having a hydrophobic part that is attached to oil. Here we have oil or grease, anything, and here we have water. It forms like this. Here we have water, this is water, and here we have hydrophilic part. This is hydrocarbon part, that is hydrophobic part. Here this is the interfacial layer. So, because of this formation of the interfacial layer, the interfacial tension lowers, and which promotes emulsification. That is why when we rub our dress, the oil will remove from the dress. The third factor is nature of liquid. That means if the molecules are having the strong intermolecular attraction, then the surface tension will be high. If the molecule is having less intermolecular attraction, then the surface tension will be less. If you take water molecule, we know that we have already seen this one. The water molecule is having strong hydrogen bonding. Because of strong hydrogen bonding, the intermolecular forces are strong. Since the intermolecular forces are strong, the surface tension of water will be high. In the case of ethanol, the intermolecular attraction, the hydrogen bonding is not that much strong. Therefore, the surface tension will be less compared to water molecule. Here we have the surface tension value of water, that is 7.57 into 10 power minus 2 Newton per meter, and the ethanol is having 2.227 into 10 power minus 2 Newton per meter. This is about the factors affecting surface tension. They are temperature, impurities, and nature of liquid. Here in this session, we discussed about the consequences of surface tension and the factors affecting surface tension. With this, we wind up this session. Thank you.